the quantum world. We're talking electrons, antimatter, even getting into some of the spookier stuff like quantum entanglement.
Yeah, it's definitely a heady area. And, it seems like whenever these concepts come up, there's always a lot of confusion and misconceptions floating around.
Well, you've brought us some really interesting questions from an AI conversation, so let's dive right in, shall we? The first one that really caught my eye was, why aren't two electrons in the same orbital with opposite spins considered antimatter? At first glance, it does seem to make sense, right? Like opposites should attract, or I don't know, something like that.
Yeah, it's a pretty common assumption. But the key here is that to be classified as antimatter, a particle has to have the exact opposite charge as its counterpart.
Okay, so it's not just about being opposite in any way, it's specifically the charge.
Exactly. So while those two electrons might be spinning in opposite directions, they both still have a negative charge.
Right, right. And a positron, the electron's antiparticle, has a positive charge.
Precisely. And there are other quantum numbers besides spin that also need to be opposite for particles to be considered antiparticles, but that might be getting a bit too deep for today.
Okay, so charge is the key difference. Got it. But then that brings up another question. If they both have the same charge, why can't those two electrons in the same orbital just spin the same way? Why do they have to be opposite?
Well, that's where the Pauli Exclusion Principle comes in. It's one of the fundamental rules of quantum mechanics.
It's like a quantum traffic rule or something.
Haha, you could say that. It basically states that no two identical fermions can occupy the same quantum state simultaneously.
And just to clarify, electrons are fermions, right?
Yes. So picture an electron hanging out in its orbital. That orbital determines most of its quantum state, things like its energy level and angular momentum.
Okay, so if they're in the same orbital, they have those things in common already.
Right. So the only thing left that can be different is their spin. If both electrons spun the same way, they'd have identical quantum numbers, which would violate the Pauli Exclusion Principle.
So they're forced to spin in opposite directions just to avoid breaking that rule.
Exactly. It's like trying to fit two identical keys into the same lock at the same time the universe just doesn't allow it.
Wow, that's pretty wild. But if spin is so important for distinguishing these particles, then wouldn't it make sense for spin to be directly related to charge? Like linked somehow.
You would think so, right? But universe loves to keep us on our toes. Turns out spin and charge are actually fundamentally independent properties.
Wait, really?
Yeah. An electron will always have a negative charge regardless of which way it's spinning. Same goes for positrons, always a positive charge regardless of their spin.
Hold on, now that feels a little counterintuitive. We just talked about how those two electrons in the same orbital have to have opposite spins because of that exclusion principle. It seems like they're connected.
I know, it's almost like the universe likes to be complicated. But remember, that principle is all about identical particles, making sure they're different in at least one way.
So the connection isn't direct. It's more about maintaining this kind of fundamental rule.
Exactly. It's about distinguishability. It's like, okay, you two electrons can share an orbital, but you have to spin in opposite directions so we can tell you apart.
Okay, so independent, but still doing this weird dance because of that principle. Fascinating. But if they are truly independent, are there any examples where spin and charge are not even remotely related?
Absolutely. A neutron, for example, has spin but no charge at all.
Oh, interesting. So in that case, you can clearly see how spin and charge exist completely independently.
Exactly. They're their own things, doing their own thing.
All right, so we've got these two electrons in an orbital. They're spinning in opposite directions thanks to the Pauli exclusion principle, and their charges are independent of all that. So where does antimatter fit back into all of this? Does that principle apply to antimatter too?
Absolutely. Antimatter particles are also fermions and have to follow the same rules.
So even in the antimatter world, that principle holds true.
It does. In fact, you can have two positrons in the same orbital, and guess what? They'll also have opposite spins because of the Pauli exclusion principle.
Wow, so even in that mirror universe, the same rules apply. That's pretty mind-blowing.
It is. And it actually points to a deeper idea. While the universe seems to be mostly made of matter, the laws of physics suggest that matter and antimatter should behave almost identically at a fundamental level.
So it's kind of like looking in a mirror, except one reflection has a plus sign and the other has a minus sign.
Haha, that's a great analogy. But now we've got this third concept you mentioned, quantum entanglement. And this is where things get really, really interesting. It seems like a lot of people think that just because those two electrons are in the same orbital and have opposite spins, that means they must be entangled. But that's not actually true.
Wait, really? Why not? They seem so connected already.
Well, imagine flipping two coins, and they land on opposite sides, one heads, one tails. They're correlated, sure, but that outcome was basically set the moment you flip them.
Okay, so it was predetermined.
Right. With entanglement, it's different. It's not just a correlation that was set beforehand. The particles are linked in a much deeper, spookier way.
Okay, now you've got my attention.
Even if you separate those entangled particles by huge distances, measuring one instantly affects the other one.
Whoa, hold on. Doesn't that mean we could communicate faster than light? If we could somehow manipulate those entangled particles.
Haha, that's the question everyone asks, and it's one that's puzzled physicists for decades. The short answer is, unfortunately, no. You can't actually use it to send information faster than light, even though the effects of entanglement seem to happen instantaneously.
Oh man, so much for my dreams of instant intergalactic communication. But then how is entanglement different from those two coins? I mean, they were correlated too, right? How is it more than just a fancy kind of correlation?
Okay, think of it this way. With the coins, the outcome was predetermined the second they left your hand. Even if they traveled across the universe, they're still carrying out that predetermined fate. Entanglement is different because the particles haven't decided their states yet.
I think I see what you mean.
They exist in this fuzzy state of superposition where all possibilities are still in play until one of them is measured.
But then boom, it's set.
Right, it's that active measurement that forces both particles to choose their states, and they do so in a way that's perfectly correlated no matter how far apart they are.
So it's like they're sharing a secret code. And the act of measuring one particle breaks the code and instantly reveals the message to the other one.
That's actually a great analogy. It's like they're sharing a single wave function that describes their combined state, and measuring one collapses that wave function, forcing both particles to snap into a definite state.
Okay, I think I'm starting to wrap my head around that at least a little bit. But this all sounds so theoretical. Are there any real-world applications of entanglement? I mean, it can't just be a mind-bending curiosity for physicists, right?
Oh, absolutely not. Entanglement is actually at the heart of some of the most exciting technological developments in recent years. For example, it's crucial for developing quantum computers.
Quantum computers. So you're saying one day we might have computers powered by this spooky action at a distance.
Exactly. By harnessing the power of entangled particles, quantum computers can perform calculations that would take classical computers billions of years to complete.
Wow, that sounds incredible. But what about something a little more practical? Something that could affect our everyday lives.
Well, there's quantum cryptography, which uses entangled particles to create unbreakable encryption keys.
Unbreakable encryption, how does that work?
It's based on the idea that any attempt to eavesdrop on the communication would disrupt the entanglement, immediately alerting both the sender and the receiver to the intrusion.
So it's like having a secret conversation where the walls have ears, but those ears instantly give themselves away the moment they try to listen in.
Haha, that's one way to put it. But yeah, quantum cryptography could revolutionize online security, making it virtually impossible for hackers to steal sensitive information.
Okay, now that would be a game changer. Anything else out there? Maybe even something a little more, sci-fi.
Well, there's the mind-boggling concept of quantum teleportation. Now, before you get too excited, it's not about beaming people or objects across space like in Star Trek,
Aw, shucks.
but it is about transferring the quantum state of one particle to another particle, using entanglement as the bridge.
Wait, so you're telling me we can essentially copy and paste the identity of a particle to a different location using entanglement?
In a way, yes. It's like taking all the information that defines one particle and instantly transferring it to another particle, even if they're separated by a large distance.
Okay, my mind is officially blown. So we've got quantum computers, unbreakable encryption, and maybe even the building blocks for something like teleportation. It sounds like entanglement isn't just a theoretical curiosity, it's the key to unlocking a whole new era of technology.
Absolutely. It's a testament to the power of quantum mechanics and its potential to completely revolutionize our understanding of the universe and our place within it.
But before we get too lost in the future, let's circle back to something we touched on earlier, antimatter. We talked about how that Pauli Exclusion Principle applies to antimatter as well, and how it behaves almost identically to matter at a fundamental level. But if that's the case, why is there so much more matter than antimatter in the universe? Shouldn't they have been created in equal amounts during the Big Bang?
That's a fantastic question, and it's one of the biggest mystery in cosmology. It's called the matter-antimatter asymmetry problem. If matter and antimatter truly were created in equal amounts, they would have annihilated each other, leaving nothing but a sea of energy.
So the fact that we exist at all means something must have happened.
Exactly. The universe is filled with galaxies and stars and planets, which means something must have tipped the scales in favor of matter.
So what could have caused this imbalance? Why didn't everything just cancel out?
That's what physicists are trying to figure out. There are a lot of theories out there, but so far, no definitive answer. One possibility is that there's a subtle asymmetry in the laws of physics that favors the creation of matter over antimatter.
So our very existence could hinge on a tiny imperfection in the laws of the universe. That's both terrifying and fascinating. It seems like we've covered a lot of ground today, from the Pauli Exclusion Principle to entanglement to this mind-boggling mystery of missing antimatter. And somehow it all seems connected, like different threads in the tapestry of the quantum world.
It really is remarkable how these seemingly disparate concepts are all intertwined. And who knows what other connections and mysteries are still waiting to be discovered out there in the quantum realm.
Okay, so we've talked about how entanglement happens. It takes this special interaction, this quantum handshake. But once those particles are entangled, what does that actually mean? Like, what are the implications of all this?
Well, it means that those particles are no longer independent. They basically become part of a single interconnected system, no matter how far apart they are. And that's where things get really mind-bending.
Yeah, that's the spooky action at a distance that always gets me.
Exactly. So let's say you measure the spin of one of those entangled electrons, and you find it spinning up.
Okay, I'm following.
That means the other entangled electron instantly flips to spin down, even if they're light years away from each other.
Whoa, so they're like linked by some invisible force. It's like they're sharing a single destiny or
It
something.
really is. And it doesn't matter how far apart they are, that connection remains. It's like that glove analogy we talked about earlier, remember? You open one box and find a right-handed glove.
Right, and then instantly you know the other glove is left-handed.
Exactly. Even if that other glove is billions of light years away.
Okay, so that's definitely mind-boggling, but here's something I'm still struggling with. If we can't use entanglement to send information faster than light, then how is it any different from those two coins we talked about? You know, the ones that landed on opposite sides, they were correlated too, right? How is this entanglement thing more than just a fancy kind of correlation?
Okay, good question. Think about it this way. With the coins, the outcome was basically predetermined the moment they were flipped, right? Even if they traveled across the universe, they're still just carrying out that predetermined fate.
Right, they're just following the path they were set on.
Exactly. Entanglement is different because the particles haven't actually decided their states yet. They're in this fuzzy state of superposition where all possibilities are still in play until you measure one of them.
Okay, so it's like until you look, they could be anything.
Exactly. And then boom, it's set. It's that active measurement that forces both particles to choose their states. And they do so in a way that's perfectly correlated no matter the distance between them.
So it's like they're making that decision together, even though they're separated.
In a way, yeah. It's like they're sharing this secret code, and the act of measuring one particle breaks the code and instantly reveals the message to the other one.
Wow, that's a great way to put it. So it's not just that they're correlated, it's that their fates are intertwined in this really deep way.
Right, they're sharing this single wave function that describes their combined state. And measuring one particle collapses that wave function, forcing both particles to snap into a definite state.
Right, I think I'm getting it. But this all sounds incredibly theoretical, you know? Are there any real-world applications of entanglement, like something beyond just blowing our minds?
Oh, absolutely. Entanglement is actually at the heart of some of the most exciting technology being developed right now. For example, it's crucial for building quantum computers.
Quantum computers. So you're telling me that we might one day have computers that are powered by spooky action at a distance?
Exactly. By harnessing the power of entangled particles, quantum computers could perform calculations that would take classical computers billions of years to complete.
Wow, that's incredible. But what about something a bit more down to earth? Something that could affect our daily lives?
Well, there's quantum cryptography, which uses entangled particles to create unbreakable encryption keys.
Unbreakable encryption? That sounds like something straight out of a spy movie.
It kind of is. The idea is that any attempt to eavesdrop on a communication would actually disrupt the entanglement. And that would instantly alert both the sender and the receiver that something's up.
So it's like having a secret conversation where the walls have ears, but those ears immediately give themselves away if they try to listen in.
Haha, exactly. Quantum cryptography could completely revolutionize cybersecurity, making it virtually impossible for hackers to steal sensitive information.
Okay, that would definitely be a game changer. Is there anything else? Any other mind-blowing applications out there?
Well, there's also this idea of quantum teleportation. Now, before you get too excited, it's not about beaming people or objects across space like in Star Trek.
Oh man, that's too bad.
But it is a way of transferring the quantum state of one particle to another particle using entanglement as this kind of bridge.
Wait, so you're telling me we could essentially copy and paste the identity of a particle to a completely different location using entanglement?
In a way, yeah, it's like taking all the information that defines one particle and instantly transferring it to a completely different particle, even if they're separated by a huge distance.
Okay, I think my mind is officially blown. So we've got quantum computers, unbreakable encryption, and maybe even the building blocks for teleportation. It sounds like entanglement isn't just a theoretical curiosity, it's the key to unlocking a whole new world of technology.
Absolutely. It really showcases the power of quantum mechanics and its potential to revolutionize our understanding of the universe and our place in it.
Wow, that's a lot to take in. But before we get too lost in the future, let's circle back to something we touched on earlier, antimatter. Remember we talked about how that Pauli exclusion principle applies to antimatter as well, and how it basically behaves just like matter at a fundamental level.
Right, like two sides of the same coin.
Exactly. And if that's true, then why is there so much more matter than antimatter in the universe? Shouldn't they have been created in equal amounts during the Big Bang?
That is a fantastic question, and it's one of the biggest unsolved mysteries in physics. It's called the matter-antimatter asymmetry problem. If matter and antimatter were truly created in equal amounts, they would have completely annihilated each other, leaving nothing but energy.
So the fact that we're here at all means something must have gone differently.
Exactly. The fact that we have galaxies and stars and planets means that something must have tilted the balance in favor of matter.
So what could have caused that? Why didn't everything just cancel itself out?
That's what physicists are trying to figure out. There are lots of theories, but no definitive answers yet. One possibility is that there's some subtle asymmetry in the laws of physics that favors the creation of matter over antimatter.
So our very existence could be because of a tiny imperfection in the universe that's both amazing and a little bit scary.
It really is. It just shows you how much we still don't know about the universe and how much there is still to discover.
You know, it's pretty wild to think about all this crazy quantum stuff happening all around us constantly. Like it's happening right now in this room.
I know, right? It's like a whole other world operating right under our noses.
It makes you realize that even something as simple as like two electrons in an atom can lead to some pretty mind-blowing physics.
Definitely. And we've only just scratched the surface today.
Well, let's try to sum up what we've learned, right? We started with that question about why two electrons in the same orbital with opposite spins aren't considered antimatter.
Right. And the key takeaway there was charge, right? Antimatter has to have the opposite charge as its matter counterpart.
So even though those two electrons are spinning in opposite directions, they both have a negative charge. So they both still just regular matter.
Exactly. Charge is the defining factor when it comes to antimatter.
And then we got into the Pauli Exclusion Principle, which explains why those electrons have to have those opposite spins in the first place. It's like there's this rule that says no two identical fermions can be in the same quantum state at the same time.
Yeah. It's like a fundamental law of the universe, you know? And it applies to all fermions, not just electrons. Even the ones in the antimatter world have to follow this rule.
So that principle, that's what forces them to have those opposite spins, just to avoid breaking that cosmic rule, right?
Exactly.
But then, of course, we learned that spin and charge are actually independent of each other.
Yeah, that one's a little counterintuitive, I know.
It really is. It feels like they should be connected somehow, you know?
You'd think so, but the universe likes to keep us guessing.
Haha, no kidding. And then, of course, we went down the rabbit hole of entanglement.
Ah, yes, entanglement, where particles become linked in a way that just seems to defy logic.
Like, measuring one instantly affects the other one, even if they're miles apart. It's wild.
It really is. And we talked about how it's not just a simple correlation, it's something much deeper than that.
Right. It's like their destinies are intertwined.
Exactly.
And we even talked about some of the potential applications, like quantum computers and unbreakable encryption and even teleportation.
The possibilities with entanglement are really mind-boggling.
No kidding. And then, you know, just when we thought we had a handle on all that, we circled back to antimatter and that whole mystery of why there's so much more matter than antimatter in the universe.
Right, the matter-antimatter asymmetry problem, one of the biggest unsolved mysteries in physics.
It's crazy to think that our very existence might hinge on some tiny imperfection in the laws of physics.
It really makes you appreciate the delicate balance of the universe, doesn't it?
It does. So I guess the big takeaway from all of this is that the quantum world is a truly strange and wonderful place. And the more we learn about it, the more we realize just how much we don't know.
Absolutely. And that's what makes it so exciting, right? There's always more to discover, more mysteries to unravel.
Well, on that note, a huge thanks to you for joining us on this deep dive into the quantum realm. And to all our listeners out there, thanks for tuning in. Keep those questions coming, and most importantly, never stop exploring the wonders of the universe.